Right now, light is hitting your eyes that began its journey inside the sun. Let's follow a single particle of that light from the very beginning to the very end. At the very center of the sun, temperatures reach around 15 million degrees Celsius, and pressure is immense. Under these conditions, hydrogen nuclei are forced together in a process called nuclear fusion. They fuse into helium, and in the process, release a tiny burst of energy, a single photon of light. This is the moment our photon is born, a high-energy gamma ray, right at the very center of the sun. This same reaction is happening on a massive scale. The sun converts roughly 600 million tons of hydrogen into helium every single second. And our one photon is just a single result of that enormous process. You'd think a photon, moving at the speed of light, would escape the sun almost instantly. It doesn't. The sun's interior is so incredibly dense that our photon can only travel a tiny distance before slamming into a particle. It gets absorbed and re-emitted, over and over again, in a completely random new direction each time. This is called a random walk. Because the path is so random and indirect, this journey to the surface takes an astonishing amount of time. Estimates vary widely depending on the model used, but it likely takes somewhere between tens of thousands and a few 100,000 years for a photon to escape the sun's interior. This slow, random walk region is called the radiative zone. But closer to the surface, conditions change, and the sun's material actually starts to physically churn and boil, in a layer called the convective zone. In this zone, our photon essentially hitches a ride, carried along by huge, slow-moving currents of hot plasma rising and falling, not unlike a pot of boiling water, just on an unimaginably larger scale. Eventually, after countless collisions, our photon reaches a layer called the photosphere, the sun's visible surface. Here, the gas is finally thin enough that the photon can travel in a straight line, completely uninterrupted, and escape into space. Along the way, all those absorptions and re-emissions have shifted its energy down. From a high-energy gamma ray into the visible light we can actually see. The photosphere itself sits at roughly 5,500 degrees Celsius. That's dramatically cooler than the 15 million degrees at the core, but still hot enough to instantly vaporize anything we're familiar with. After thousands of years trapped inside the sun, the rest of the journey is almost absurdly fast by comparison. Once free, the photon travels through the near-total emptiness of space at the speed of light. The distance from the sun to Earth, about 150 million kilometers, takes only around 8 minutes to cross. 8 minutes. After tens of thousands of years trapped inside the sun. That contrast is really the strangest part of this whole journey. Space between the sun and Earth is an almost perfect vacuum. So unlike its chaotic journey inside the sun, there's essentially nothing for the photon to collide with. It just travels in a straight, undisturbed line. This is also why, if the sun somehow suddenly vanished, we wouldn't know about it for a full 8 minutes. We're always seeing the sun exactly as it was several minutes in the past, never as it is right now. As our photon approaches Earth, it enters the atmosphere, a thin layer of gas surrounding the planet. Inside the atmosphere, it can bounce off gas molecules, a process called scattering. This is actually what makes the sky look blue during the day. But most photons, including ours, pass through relatively undisturbed and continue on toward the ground. This same scattering effect is also why sunsets look red. At sunset, light has to travel through much more atmosphere at a low angle, scattering away almost all of the blue light and leaving mostly red and orange behind. After its long journey, the photon reaches your eye and passes first through the cornea, the eye's clear outer layer. It then passes through the lens, which bends and focuses the light precisely. The photon finally lands on the retina, a light-sensitive layer lining the back of the eye. There, it strikes a photoreceptor cell, triggering a chemical reaction that converts the photon into an electrical nerve signal. Your retina actually has two different types of these photoreceptor cells. Rods are extremely sensitive to brightness and motion, especially in low light, while cones are what let you perceive color and work best in brighter conditions. That signal travels down the optic nerve to your brain, which interprets it as part of the image you see. And with that, the photon's journey ends. Tens of thousands of years trapped inside the sun. 8 minutes crossing space. A fraction of a second to become part of your vision. Every single time you look at sunlight. This entire journey has just taken place. Thanks for watching. Subscribe for more science visualized.